Well, hello, Chem students. Let's get started with today's lesson on the quantum model of the atom that can be found in lesson 12 in your study guide. So get that out and let's get started. All right, lesson 12, the quantum model of the atom. Now, today's focus is going to be on our current model of the atom. This is known as the quantum model or the wave mechanical model, or even sometimes called the electron cloud model. We'll use various names, but nevertheless, it is the same model. Now, before we dive into the quantum model, I want to quickly review the Bohr model a little bit with you. Remember that Niels Bohr is going to be the very first physicist slash scientist to take the atom structure and to build a model around quantum theory. And so Niels Bohr is often thought of as the father of quantum model of the atom. All right. Now, Bohr's going to focus on the electrons. He's going to realize that the electrons seem to exhibit some kind of quantum behavior. And so he's going to say that electrons have a specific quantity of energy and that there are specific quantum levels or energy levels in the atom, meaning that the electron can only be at specific locations within the atom. They just can't be anywhere they want, but they are at specific locations. And those locations we know are energy levels or shells. Now, an electron, according to Bohr and his model, electrons can never be in between the electrons' shells, much like the steps on a ladder or on a steps on a staircase, that they can be at step 1 or step 2 or step 3, but it can never be, the electron can never be in between those steps. And so Bohr, he's going to be really this first one to really bring in the fact that the electron is quantized and the atom itself is also quantized. The problem is that the Bohr model, well, we're on the right track, but yet we're wrong. Okay, we're not there, and that is because Bohr again was really focusing that the electron is a particle. He did not bank on the fact that electron is both wave and particle, and therefore his mathematics never counted for the wave nature of the electron, only the particle nature of the electron. So when we started applying the Bohr model to other atoms besides hydrogen, things just didn't quite work out the way that was expected. Again, because we were treating the electron solely as a particle and not as a wave-particle duality, okay? And therefore, the Bohr model never accounted for Heisenberg's uncertainty. So today's model, the current model that we currently hold to, the quantum model or the electron cloud model or the wave mechanical model, all of those takes into fact that the electron is both a particle and a wave at the same time, and the Heisenberg's uncertainty principle. Okay, so without further delay, let us dive into our current model, the wave mechanical model of the atom. So this model was developed by a physicist named Erwin Schrödinger. Erwin Schrödinger used some very complicated mathematics, statistical mathematics, in order to basically describe the electron in its wave particle nature and the result of the uncertainty principle as a result of the wave particle nature of the electron. All right. To do that, he had to make some really weird thinking about the electron. And so we are not going to focus really on the mathematics, these equations that Schrodinger used. They're above our classes of where we're at, okay? So just forget it. We're not going to go there, okay? But what we are going to do is focus on the solutions of Schrodinger's equations, the results. Like, the results have the meaning that we need to look at here. And those results are known as the wave function, or he used the wave function as a way of describing the wave particle nature of the electron in the atom, okay? So we're going to look at the wave function and what that all means here in just a moment. So the bottom line is, what is the electrons doing in these atoms, okay? What's our current understanding of the electron? Well, being the fact that it is expressive as a wave and particle at the same time, it's a little difficult for us to do a measurement where we can see the wave and particle nature of the electron at the same time. Once we begin to make any type of measurement, the electron is either going to choose to be in the wave state or the particle state, all right? So what we have found is we need to start making our measurements of electron based on its wave state. And so that's what we've kind of done. So what we're going to do is we're going to see that the best way to describe the atom, or sorry, the electron in the atom, is by thinking of the electron as a wave. And therefore, it's going to be a standing wave with only certain allowed oscillations, okay, as that electron basically is a wave, okay? Because we know the electron's wave state or nature, the electron's energy then can be accurately known. And that goes along with Heisenberg's uncertainty principle, is that if we know the wave nature of it, we can determine the energy accurately. But what we can't do is determine the electron's position accurately. And so we are uncertain where the electron will be at any given time. Okay, that's kind of the problem with Heisenberg's uncertainty principle based on the wave particle nature of the electron. We also know that the electron is quantized. That is, that it can only have certain values of energy, and we've discussed that before. All right, so here we get a little bit into position, a little bit about trajectory of electrons or particles in the classical sense versus the quantum sense, okay? So since we cannot know the position and the velocity of an electron simultaneously, we cannot know its trajectory, okay? So in other words, we cannot determine at any given time where an electron in motion would land or where it would be at any given time. All right, again, based on Heisenberg's uncertainty principle. In quantum mechanics, then, trajectories are replaced with what we call probability distribution maps. We're going to look at those very closely in a moment. A probability distribution map is a statistical map that shows where an electron is likely to be found under a given set of conditions. So I'll come back to the rest of this, but let me kind of talk to you about trajectory in the classical sense. So if you think about a baseball in classical sense, it is a particle, and therefore it should act like any normal particle. If a baseball player hits the baseball with a bat, it should have a particular trajectory. And we should be able to use classical physics to explain the location, the velocity, so the energy that the baseball has at even given point in time, okay? So we can even know, based on the calculations, where the baseball should land. So if, for instance, in this particular diagram that we're looking at here, if my baseball starts at point A, it could be on a trajectory that it would land at point C. And I could determine not only when it would land at C, position C, but that it would definitely land there, and I can make that prediction. Or maybe it's on a pathway that it will actually land at B, position B. And again, I can determine the time. I can determine essentially the exact spot at B that the baseball should hit, okay? Now, if you think of electrons as particles behaving in a classical sense, then the prediction of where an electron could be in an atom is possible, okay? But the problem is the electron is not just a particle, it is a wave. In fact, is when we make the measurements of the electron in an atom, we're really usually seeing the wave nature of the electron. And therefore, all of this trajectory stuff is out the door. We can't determine an exact position at any given time where the electron will be, okay? Instead, the best that we can do is make a possible probability prediction, okay? In other words, we're going to use what is called the wave function that Schrodinger is going to use. And the results of that basically gives us a generally idea or a probable idea of where the electron might actually be in the atom. Not where it will be at any given time, but where it might be, or the probability of where it might be at some instant in time. And so what we get is something, a graph shape of the wave function. Let's see if I can draw some things here. So essentially, if you look, we would say that this on the x-axis is the distance from the nucleus. So in other words, the distance of the electron would be from the nucleus. And on this axis is the wave function. This is the sign for the wave function, but it's squared, okay? And Schrodinger is going to square it. All right, and we're not going to get, again, into all the details of the mathematics of this. You can do that research on your own if you want to. But the point is that the electron can be at any distance according to this particular electron that we're looking at, can be at any point in this, under the area of this curve, essentially. So anywhere from these distances, the electron can be at, okay? But the question is it have an equal probability of being at any given point? And the answer is actually no, all right? There are some places that the electron has a more probable place of being than at some other point. And that is, you can say, you can take the high point, which you could say the area under this portion of our curve is the largest area, which means that this gives us the highest probability that at this distance, somewhere in here, that the electron has the highest probability of being at in the atom, okay? Now, that doesn't mean it can't be at these other distances. Absolutely, we could find the electron somewhere in between here and here, okay? In between these distance points, okay? But if we were going to be a gambling man, we would probably say, well, where's the highest probability that where the electron could be at? And that is indicated by the wave function is somewhere in here, okay? Now, and this area can get smaller and smaller, so we can really pinpoint where the highest probable location that the electron could be found, where its position is, all right? Now, if I take this curve and I kind of basically create an image out of it, I get something that looks like this that you're seeing here, okay? that I'm just kind of doing a terrible circle with, all right? This is a probability distribution curve or map, okay? Now, I'm going to come back and talk a lot more about this in just a moment, but what you could say is that where all these dots that you see is probability points where an electron might be located at some given time. And where there's a higher density of dots, right, and what you can see right here towards the middle, is where the highest probability of where you're going to see an electron. So the more dots that are plotted in a picture using the data from this curve, the more likely you're going to pinpoint where the electron might have the best chance of being found, okay? So what you're seeing here is probably what Bohr would have said was an energy level. All right. So where the most probable distance, where the high probability chance is where Bohr would have placed his energy levels at. Okay, but again, they're not well defined. Okay, and that's because again, an electron being a wave, it can be at multiple locations, really multiple locations even at the same time, and so it's very, very complicated in that manner of pinpointing the position of the electron. It can be anywhere in here at these particular points, but it's most probable here, which is going to be our defined energy level. Okay, so again, this is sort of what this would be a solution, or the wave function solution to Schrodinger's equations would be these probability distribution maps that you're seeing right here, okay? Okay, I'm gonna go back and finish this up. So in summary of all of that, the wave function then gives us information on the statistical probability of finding an electron in a specific region of space in the atom, okay? A specific region of space in the atom. Now, this region, you just saw, we take the data from the graph and from the equations, and we basically can draw a picture of it. And we essentially kind of get a sort of a defined space a little bit, and that's going to be called an atomic orbital, essentially. And within that atomic orbital, that's where we have somewhere in that orbital, we have a probability of finding the electron, okay? Now, an electron that's going to be somewhere in that region, that orbital space, okay, that you could say, the electron is going to have a quantized energy. Okay, I lost my light here. Oh, geez, those sensors. Okay, the electron is going to be quantized in that space. It's going to have a fixed quantity of energy, and as long as it's in that space, it's not going to lose any energy. Very much like Bohr predicted with his energy shells, that as the electron is moving around that energy shell, it really is not going to lose energy while it's there at all. It's just going to keep on doing a circular motion. But here, we don't really have circular motion because really these are waves, and the electron could be anywhere in a specific region, probability region, okay, or an orbital. Okay, but as long as that electron is somewhere in that orbital, and also we call them electron clouds sometimes, somewhere in that cloud, it's going to have a fixed quantity of energy. Okay, we'll get more into this here. Show you lots of examples. Okay, so let's really quick overall summarize the Bohr model. Since we're back here with Niels Bohr. Again, Bohr said, hey, got a nucleus, Rutherford It's right about that. And then the electrons, though, they can only be at specific distances from the nucleus, and these specific distances are known as energy levels. And these energy levels are, because they're at specific distances, the electron is quantized. It can have energy in level 1, or energy in level 2, or energy in level 3, but it cannot ever be in between the energy levels. Therefore, it can never have those energies, is what Bohr is essentially saying. However, Born says that electrons, if they're in these stationary states, these energy levels, they're going to continue to have that same quantity of energy without losing it, but they can absorb energy and transition or jump to higher levels of energy, and they can lose energy in quantum packets of energy, you remember photons, and go to a lower level, okay? So it can do that, but it can never transition into areas of the atom that it's not allowed to, into the space in between these energy levels, okay? So there's the Bohr model. But compare that to our quantum model. Instead of having these nice stationary energy level states, we do have the nucleus, that's for certain. But now that the electron is behaving like a wave, we get, instead of these nice defined specific locations, we get these electron clouds. And what I'm doing, trying to do really quickly, is to draw these probability points that will eventually make up a cloud. I'm quickly trying to make just cloud here. You get, I hopefully get kind of the point here. And what we're saying is that these clouds, which are also called orbitals, and that's usually what we're going to refer them to as orbitals. Again, these are just probability points in space in the atom where the electron could be at any given time, okay? More and more and more, right? You do this all day, okay? But there are hundreds and hundreds of thousands of dots here that makes these clouds, okay? And there you go, all right? Now, at this point, then, we cannot determine if an electron is at a specific place within the atom because we can't predict its trajectory. So what we can do, though, is find where the most highest density of dots. And where those highest density dots are, let's say maybe somewhere in here, would be Bohr's energy level. So we might actually have a better chance of finding the electron near where that energy level would be, but nevertheless, it might not be there. It could be anywhere outside of that where an electron is allowed to be. Bohr is right. There are areas where the electron cannot be, right? We'll kind of look at that in just a moment. It can never be in between this electron cloud and the nucleus. It'll never crash into it, okay, at all right? So let's move on to these orbitals. All right, so what we're seeing here, we already kind of looked at this probability distribution curve, but this is a specific important probability distribution curve or map, okay? From definition, a probability distribution map is a statistical map that shows where an electron is likely to be found under a given set of conditions. Now, I'll get to electron density in just a moment. So what you're looking at is a type of cloud, a solution, and we said already that where you see these dots is a possible location where the electron could be, all right? But where we have a greater density of dots is the most probable location of where the electron could be. So for this particular electron cloud or orbital, we would most likely find the electron somewhere here in the center, okay? Now, this is also known as electron density, and we'll use the term electron density quite a bit throughout the year. The electron density is just another way of expressing probability. So where there's a higher amount of density of dots means that there's a higher electron probability of finding an electron. That's all we're saying here. So the density, electron density, is really great here, but not so great out here. So that means that the electron density is really low. The probability of finding an electron becomes lower. And so really, what we're looking at, the reason why it's so dense here is because in reality, this is very close to the nucleus. It's not the nucleus, but close to the nucleus. And we would assume that the electron would be closer to the nucleus and get less likely to be out here where the nucleus is not, or further from the nucleus is what we're saying. All right, I hope you get the idea of this. What's going on here? Now, if I was to take, and this is not going to work so well, but I'm going to try. If I was to kind of draw a kind of a deal around this, best I can, all right? This kind of seems to have sort of a boundary, because where there's no dots, and I know this is not perfect, but where there's no dots, there's no possible way for an electron to be out here. The electron is going to be somewhere defined in this region. And what I've done is define what is called the orbital then, okay? And this particular orbital has a shape to it, and it's spherical, and we call it an s orbital, okay? And let me kind of show you what an s orbital would kind of look like, all right? It's kind of like this, spherical. These points here are the x and y axes. So it's three-dimensional, and this is what you're seeing on your screen right now, is this probability distribution of the electron in an s orbital. Okay, yeah. Now, on the outside of the surface of this is where you would find the lowest electron density. But as you open this up and go inside of this s orbital, that's where you would find the highest electron density. And that's where the center point that you see. So the nucleus is actually going to be kind of in the inside of this s orbital. And the s orbital surrounds that nucleus. Okay? Hopefully you get kind of the idea. If anything, remember that this is an s orbital. Okay? That will be important. But s orbitals are not the only solutions to Schrodinger's equation or the wave function. There are other orbitals that exist out there, okay? Show you some more. All right, oh, actually, I'll skip that for the time being. Okay, what we have now is we're looking at a very weird, funky orbital. These are known as p orbitals. And what you can see is here's the probability, and you get kind of a lobe, what we call a lobe here, and you get a second lobe that looks like this, sort of, okay? So a p orbital has two lobes. Right in the center here, there's no dots. So therefore, there's no probability that an electron can exist in this space at all. So an electron can either be somewhere over here in this lobe or somewhere over in this lobe, but never in between the two lobes. Waves, right? Very crazy stuff, okay, that's going on here. So these p orbitals kind of look like a dumbbell shaped, or say a figure eight, okay? Now, the interesting thing is that there are three different, okay? There are three different p orbitals, okay? There are three of them. And the difference, and actually they're shown here, the difference in these three are not their shape, but their spatial orientation, how they're oriented in space. Some of them are going to have the two lobes oriented along the x-axis. Some of them are on the y-axis, and some of them are on the z-axis in three-dimensional space. So let me kind of show you an example. So this is a p orbital. Notice it's got the two lobes. This is a lobe, and this is a lobe. And in between the lobes, there are no possibilities of the electron existing. In fact, this is probably where the nucleus is in between the two lobes, okay? If you want to somewhat visualize it, okay? So this right here, I would call the PY, because let's say it's along the y-axis, okay? Up and down our y-axis. So again, we have X, Y, and Z is pointed out towards us, okay? So this is the PY orbital, okay? This one is going to be the PX orbital. There's our two lobes, but those are along the x-axis. So this is the PX. Now, one thing to note, really important about these two, is that they are going to have electrons that have the same energy in these p orbitals, okay? So whether the electron is in this p orbital or in this one, the py or the px, the electrons have the same energy. In other words, these orbitals have the same exact amount of energy or quantized energy, okay? That's important as we get more into this. And then we have our last one, the pz, okay? Now this one is pointed out towards the z-axis or pointed towards you, okay? This one here, as well as the other two, also have the same exact energy. So all the p orbitals are identical in energy, okay? Now, this is where things get a little complicated, okay? Each one of these is indeed an orbital. So we have the px, the py, and the pz, okay? They are individual. Now, each orbital, each one of these can have a maximum of 2 electrons in each one. So you can have 2 electrons in a px, 2 electrons in a py, and 2 electrons in the PZ. I can't even do this very well. Actually, let me just clear everything, okay? So you can have 2 electrons here, 2 electrons here, and 2 electrons here, okay? That gives us a total of 6 possible electrons in these p orbitals total, okay? Now, what really happens in the atom is that these p orbitals are actually going to combine. All of them are going to combine together. All 3 of them are going to combine together. And when they combine, they're going to form what we call a subshell. So individually, they're called orbitals, but combined as a package deal, all 3 of them, they're known as a p subshell, okay? So again, I'm going to take the x, y, and the z and put them together to make one structure called a subshell, or a p subshell in this case, because they're made up of p orbitals, okay? So you can have 2 electrons, again, 2 electrons in each one of these orbitals. So if I combine them into a subshell, I can have a maximum of 6 electrons in a p subshell. Okay? 6 electrons maximum in a p subshell, because each p orbital has 2 electrons in there. Okay? Whew. Hope that is clear, okay? All right, here's another look at a p orbital. You can see the two lobes here, and then in the middle there cannot be any electrons, okay? So let's move on to another set of orbitals. Yes, there are more orbitals. Now, there are 5 additional orbitals that are somewhat similar to one another. These are called d orbitals, okay? And as depicted in your notes and in this diagram, there are going to be 5 of them. 1, 2, 3, 4, and 5, okay? All 5 of these d orbitals have exactly the same quantity of energy, okay? And each one of them can have 2 electrons in them, okay? Just like those p orbitals, d orbitals can only have 2 electrons in them, all right? All right, so here we go, our 2 electrons, okay? These are the individual ones. The only difference between them is the spatial arrangement, okay? So here's a d orbital, okay, that you can see up here that looks like similar to your diagram. And again, you can have 2 electrons in any particular d orbital. Let me grab another one. Okay, so you can see the spatial difference, the orientation of these d orbitals. Okay, they look similar. They have 4 lobes. Each d orbital that you see here have 4 lobes. But the problem is that they are in different spatial arrangements. Okay, so they do create different orbitals. Okay, but they are called d orbitals, all of them. Now, just like we saw with the p orbitals, oh, what happened? The heck? Sorry about that. Stupid internet. Okay. Just with the p orbitals, the d orbitals are also going to combine to form a subshell. Okay, and this is what the subshell of d orbitals would look like. Again, we're going to take all 5 of those and we're going to combine them into a subshell. And this is going to be known as the, oops, it's going to be known as the d subshell. All right. And because you can fit 2 electrons in each one of those, that means that you can have a maximum total of how many electrons? 10 electrons in a d subshell. Okay, that's 2, 4, 6, 8, 10. Okay, so maximum of 2 in each one. So combined total is 10 electrons in a d subshell. Okay, so far we've seen s orbitals, and by the way, an s orbital can only also have 2 electrons in it, and the s orbital, there's only one s orbital. There's only one type of s orbital, and so really an s orbital makes up its own s subshell. Okay, so an s orbital is an s subshell with a maximum of 2 electrons. And then you have the p subshell, and the p subshell is made up of 3 p orbitals, x, y, and z. They combine together to form that p subshell. You could have a maximum of 6 electrons in the p subshell. And then the d subshell. And the d subshell is made up of 5 orbitals with different spatial orientations, each of them having 6 electrons, or sorry, each of them having 2 electrons, making a total of 10 electrons in the d subshell, or a maximum of 10 electrons in the d subshell. You can have less than that, but you but you cannot have any more than 10 electrons in a D subshell, okay? I know, this is crazy stuff, right? Hey, we're not done. Guess what? There are more subshells. Yes. There are what are called F subshells. Oh my goodness, look at these F subshells. Now, you don't have, I don't think you have a copy of this in your notes, but this is what the F subshells would look like, okay? And there are 7 of them, okay? 1, 2, 3, 4, 5, 6, and 7, okay? So you got 7 F orbitals, okay? 7 F orbitals. Each of them can have 2 electrons in them, just like any other orbital, okay? Each one of these, right? Ooh, on all these electrons. Again, a maximum of 2 electrons. They can have 1 or they can have none, but they cannot have any more than 2 electrons in these F orbitals or any orbital, okay? Well, since there are 7 of them, we can combine all 7 of them to make what? You got it, the F subshell, okay? All right, the F subshell. And how many maximum electrons? 14, right? There's 7 orbitals. There are 2 electrons in each one. That's a 14 electron total in the F subshell, okay? And all of these orbitals, F orbitals, have exactly identical energies. They just are in different spatial orientations in the atom, okay? Wow, that's it. Now, are there any more subshells? Yes, there are. Are we going to talk about them? No, we're not, okay? We're only going to focus on S subshells, the P subshell, the D subshell, and the F subshell, and that's it, okay? That's all we're going to do, okay? That's enough. So I'm going to summarize this really quick. All right, we cannot know the position of the electron in an atom. We can only know the probability of where an electron might occur. So we create these electron clouds based on statistical probability mathematics, okay? And the wave function, essentially. And as a result, we get these really interesting cloud structures called orbitals, all right? There are various different types of orbitals. Again, there are S orbitals, there are P orbitals, D orbitals, and F orbitals, and so forth, okay? Now, the S orbital, there's only one of them, right? There's only one type of S orbital that can have 2 electrons in it, maximum of 2, all right? There are 3 types of P orbitals, X, Y, and Z, different spatial orientations. They look like dumbbells, okay? Those 3 combined to form the P subshell. Since you can have a maximum of 2 electrons in each one, together it makes a maximum of 6 electrons in a P subshell. Then you have the D subshell, which is made up of 5 D orbitals, different spatial arrangements, okay? But they all have the same amount of energy and they all have 2 electrons max in them, making a total of 10 electrons in a D subshell. And then there is the F subshell, which is made up of 7 orbitals, 7, 2 electrons in each one max, making a total of 14 electrons. But each one of these F orbitals has exactly the same amount of quantity of energy, okay? They're just spatial oriented differently, but they are F subshells. They're the F orbitals that are combined to form an F subshell. Whew. All right, you got it? I hope so. All right, this is a lot to take in, I know. So think about it. Now, one last thing I want to kind of talk about before we're done with this. All right, I don't think we can take any more of this. Okay, let's go back to let's go back to our S subshell here. All right. Actually, let's even go back. Okay, let's go back to this really quick. Okay, now what I'm going to do is we're going to use lines like these little lines here to represent a orbital. Okay, so for instance, if I say an S, this would represent this line is going to be representing of the S orbital, and it's a really easy way of doing that instead of drawing this S orbital. Okay. Now, so what I'm going to do is I'm going to draw some lines based on energy. Okay. Clear this and start here. Okay. So you probably could do this in your notes somewhere. Okay. It doesn't matter where. So as far as energy goes, I'm going to draw orbitals based on an increase in energy. Okay. So energy is going to increase. So the S orbitals are the lowest in energy. Then we have our 3 p orbitals, okay? And the 3 p orbitals that combine to form the subshell, the p subshell, these have more energy, or the electrons in these orbitals are going to have more energy than in the S subshell. The D subshell, there are 5 orbitals, right? 1, 2, 3, 4, 5. Okay. The D orbitals have more energy than the P or the S. So energy is increasing. So the electron in a D subshell has more energy than an electron in the P subshell. But if you have an electron in these different P or D orbitals, they all have identical energies. And then finally, we have the F. In the F, there are 7. 1, 2, 3, 4, 5, 6, 7. The F subshell, the electrons in them have more energy than the D, the P, and the S. So what I'm saying is that based on the subshell an electron is in, it's going to have a different amount of energy. The S subshells, electrons have the lowest amount of energy, then the P, then the D, and then finally the F. The electrons in the F subshell have the most amount of energy, okay? Now, the way we're going to represent an electron in a shell is by using an arrow, like an up arrow or a down arrow, okay? We'll talk more about this in the next lesson, what we mean by up and down arrows. But essentially, we're going to represent an electron by using an arrow, okay? So you can only have a maximum of 2 electrons in any particular orbital, right? And so this is one orbital, this is one p orbital, here's the second p orbital, and another one. So this would be like the X, Y, and Z, okay, of the p orbital, making the p subshell, okay? So just to give you kind of where we're going to go. So what we're going to say then is that this electron has more energy than this electron because the p orbitals have more energy than the S orbital. And that's kind of what I'm trying to say here, okay? I'm done with this lesson. I think that you should go back and really study your notes and some of the information that I've given you here. But anyway, here we go. This is the wave mechanical model of the atom. You have the nucleus still, but then you have electrons that are in these orbitals or electron clouds, and they're just probable locations where they can be. And so if you have an energy level, okay, then you have these subshells that belong within that energy level. And you can have S subshells and P subshells and D and F subshells and so forth, okay? Now, in the next lesson, we'll tie this all together and tie this all in, okay? But this is it for now, okay? Good luck, and we'll see you later.